So in this video, I'm going to talk about programming tools. Programming tools basically carry out the mechanics of software creation within the confines of operating system and hardware environment. Um, the most simplest one, that's an assembler. That's the simplest of all programming tool. Basically, the assembler translates mnemonic instruction to the machine code. Um, Most of assembler carry out this translation in two passes over the source code. So the first part gonna partially assemble the code and build the symbol table. The second pass will complete the instruction by supplying the value stored in the symbol tables. Um, the output of most assembler is a stream of relocatable binary code. In a relocatable code, operand addresses are relative to where the operating system chooses to load the program. On the other hand, the absolute or non-relocatable code is most suitable for device and operating system control programming. So basically, the absolute code is just gonna have the fixed address in the memory. When the relocatable code is loaded to for execution, special register gonna provide the base addressing. Um, Basically, the addresses specified within the program are interpreted as offsets from the base address. So here's an example of the Marie code. We have the source code right here written in the Marie ISA. We have the loss X, add Y, store Z, and so on. Okay, so this is an example of the Marie code. So we can, after we assemble this code, the code gonna have this kind of a structure right here. We should note that the plus sign right here just indicate the relative offset, okay? Just not the addition, but just the indicate the relative offset, okay? So for example, if the program load into the memory with the starting address is OH 250, so you can see that with the offset of 4, the memory content of the first instruction gonna be a 1 to 54. Okay, so the first one right here, that's gonna be indicate the instruction, and here the offset in the memory. So because it's starting at the address 250, so with offset 4 is gonna be a 254. The second instruction right here gonna 3, and the offset in the memory gonna 0 5. So we're gonna have the instruction gonna 3 255, and this is gonna be a 2 and the offset gonna 6 gonna be 2 256. Okay, here's no offset gonna be the same, and so on. On the other hand, if the program loads to the memory starting at the address of OX400, for example, the same right here, you can have the first one, that instruction code right here is 1, and also the offset gonna be a by 4, so gonna 404, because it's starting at 400 and we have the offset of 4, so we're gonna 404. The second one gonna 405 because the offset gonna be 5, and so on. Okay, so basically that's the relative offset gonna be interpreted by the assembler. The process of assigning physical addresses to program variable is called a binding. So basically, a binding can occur at the compile time, load time, or run time. At the compile time, binding gives us a absolute code. Okay. On the other hand, the loading time the load time binding assign physical addresses as the program is loaded into the memory, and with the load time, the binding, the program cannot be moved. Okay, so that's gonna fit into that address. And on the other hand, the runtime binding require a base register to carry out the address of the mapping. So basically, it's a translation from a logical process address to a physical address. In most of the system, binary instruction must pass through a link editor, or we call it linker, to create an executable module. So basically, the link editor incorporates the various binary routines into a single executable file as a code for a program external symbols. Um, the same as the assembler, a linker or link editor perform two passes. The first one, the first part is to create a symbol table, and the second part gonna resolve a reference to the value in the symbol tables. So basically here a graphical representation of a linker that's used to combine related program file into a unified loadable module to the main memory. So basically the source code right here, you can see that the main program is including multiple external modules. So for example, procedure A right here gonna have the different represented in a different module right here, this procedure A. So the linker gonna combine the main program with the external module right here into a unified program that's gonna be go through the loader and gonna be loaded into the main memory for executable. So that's the task of the linker. We also can have the dynamic linking, is when the link editing is delayed until the loading time or at the runtime. So basically, in this approach, the external modules are loaded from the dynamic link library or DLLs. Okay, so the load time dynamic linking slow down the program loading, but the code to the DLL is much faster. Also, the runtime of dynamic linking occurs when an external module is the first call, and that may cause a slower execution time. However, the dynamic link make the program module smaller. However, that can carry the risk that the programmer may not have the control over the DLL. Okay, so that is some pros and cons of the DLL. Assembly language is considered as a second generation of the programming language, or second GL, and the compiled programming language such as C, C++, Pascal, Combo, or consider a third generation of the programming language, and each of the language generations present a problem that's solving tools that are closer to how people think and further away from how the machine implementation of the solution. So here's a graphical representation of the different generation of the programming language. So we can see that's got a pyramid architecture, where the first generation programming at the bottom right here, that's got a binary machine code, and we have the second generation right here, that's the assembly code, and the third generation right here, Java, C, C++, and so on. That's the third generation. The fourth generation right here, that's the SQL, libs, and so on. And the fifth generation language here is got natural language, that you can see that the ease of a human understanding gonna go up from the bottom to the top. Okay, so in this way, this language is easier for a human being to understand. But the lower layer right here, that's gonna go to the machine, so the machine gonna quickly to carry out that kind of instruction. Excuse me. So compiler basically is just a bridge of the semantic gap between the higher level programming language and the machine binary instruction. Most of compiler effect this translation in 6 phases process. The first 3 are just the related to the analysis phases. The first one we call just a lexicon analysis. So basically, in this step, we the system gonna extract the tokens, for example, reserve the word and also the variables. The second phase is the syntax analysis. So basically, just a parsing, check the statement of the construction. The third phase is that the semantic analysis. So basically, check the data types and the validity of the operators. That's the first three phase of the analysis. The last three compiler phases are the synthesis phases. So the fourth one gonna intermediate code generation. So basically, in this way, we the system gonna create three address code to facilitate the optimization and translation of the code. The fifth one, that's the optimization. So this step or this phase create the assembly code while taking into account the architectural feature of the system and organize the code so that they can make the code more efficient. The last step gonna be code generation. That's basically create the binary code from the optimized assembly code in such so that the machine can execute the code. So through this modularity, compiler can be written for various platforms by rewriting only the last two phases. So here's an example of the phases in the code. So basically, you can see that the source code right here gonna go through the first phases. That's the lexicon analyzer, and they're gonna create the token stream, and gonna go into the syntax analyzer. So this one gonna basically create the pair. The parse tree, and then gonna go into the semantic analysis. Gonna check all of the validity of the operation, and then we're gonna go into the intermediate code generator. The output of the intermediate code generator gonna go into the code optimizer, and then the code generator that will create the machine code right here. The hardware can execute. So as you can see, the symbol table right here gonna be a central interact and communicate and link with the different phases in order to make sure the information transfer among the all of the variables, and also the processors correctly. So we can see that interpreter produce executable code from source code in real time and online, one line at a time. Consequently, this will not only make the interpreted language slower than the compiled language, but it also afford less opportunity for error checking. Basically, interpreted language are very useful for teaching programming concept. This is because feedback is nearly instantaneously, and performance is really a concern in such a situation. So if we teaching a programming language, some interpreted language can be used. That's gonna give the very intuitive how the machine perform the task. Okay, so that's basic some information about the programming tool. We can find more detailed programming tool in the textbook.